From the beautiful South Studios of Way Happy, this is Mr. Meyer, and we're talking about Chapter 1.1. So, let's talk about some really quick maths here for you to learn. We are going to talk about different types of models. We're going to talk about the zero product property, and we're going to talk about graph or failure, which is just something you want to notice about your calculators. But before I go on to that, let me mention right here, page 66. Why did I scribble that out? I have no idea. I meant to highlight. What I wanted to say was page 66. I want to make sure to remind you, be working on the Chapter P review red problems. They're red numbered problems. In fact, I think I have it here on my textbook. You can see page 66, and you can see some of these numbers are black, but as you can see, like number 18 right here, that is a red numbered problem. So those are the ones I want you to do. So on your own time, kind of fit those in when you have some extra time, which I know you don't have all that much extra time, but if you could, and I'll probably give you a little test on it sometime by the end of the week or maybe next week. And so that's our goal. So make sure that you get those red numbered problems. You can also do the online textbook. Just look for the Chapter P review. All right, now why on earth, or what are we talking about here? All these different models. I just want to let you know something you probably already have discovered in your math lives is that math loves to study data, right? And what we do when we study numbers and data and we get all that info, we like to throw it into a model. And what I mean by a model is I want to make an equation out of it. I want to figure out if then I can predict things that are going to happen in the future. You know, if I can show you a model, an equation that makes this true for a lot of data, then maybe we can see what's going to happen or what maybe happened way before. We can make guesses, and it's really interesting. So there's a lot of different types of models. The first one I'm going to mention is what's called a numerical model. That's just a list of data. So last year I pulled out some statistics of one of the NFL seasons, one of the NFL weeks, and what happened. And you can look here is right here, this carried and this yards is the thing I was interested in when I looked at it. Carries is how many times a guy actually carries the football, and yards is how many yards he ran through all those carries. And I kind of noticed that if you start down at the bottom, 18 carries got you 100 yards, 20 carries got this guy 104, 24 got 106. You could see this little pattern of the more carries you got, the more yards you got. And it held true for most of the guys, except for, of course, the Rams guy right here. He had very few carries, but a ton of yards. And it wasn't perfect. Our models aren't going to be amazingly awesome, but they're going to be good judges. So I could take all this data and I could scatter plot it. I could make this my x's and this my y's, and I could graph this data, and I could try to find a line of best fit or maybe a parabola of best fit. I could find some model of this data, and then later on we could work on and make guesses of what would happen if you carried the ball 40 times. Would that be a wise thing or would it not? Maybe we could correlate the number of touchdowns in there too or something. So this is just a numerical model. When you look at a bunch of numbers and you want to sit there and take some data and make an equation out of it, look for a pattern, anything, those are numerical models. We also got what we would call algebraic models, which kind of feels a lot like a numeric model, but it's when we make that equation from that numerical model so we can do stuff with it. And so here was just one I pulled out of I don't know where, but it says in 1950 the world population was, oh my goodness, 2.5 billion, with a growth rate of about 1.68%. And so what was the population in 1955? Well, the cool thing was, if you know a formula that you've ever been given, I think I have it scrolled down right here. Oh, no, I don't. Well, you kind of see it here. One of those common formulas is you take the initial population and then you use Euler's number and you raise that, like it's an exponent. Euler's number gets an exponent, and your exponent is the rate that it is growing by, the decimal equivalent of that rate. Don't use the percent. And the time, usually in years, or whatever the rate was given at. Ours was, a rate of approximately per year, it should have said. You could type all that in and you could make it a prediction of what you think the population was. So again, this is Math Geeks taking a bunch of numbers of population of the world and then trying to make a formula for it. And this would be our formula, right? And then we would plug in the numbers and get our calculator out, and look what it tells us. There's 2.8 billion people 5 years later. 2.77 to be exact, right? Or closer to exact. And it turns out that that was a pretty good estimation. So you can see here that our calculator, what we would guess is that, and what the actual population was that. And so that's why math geeks love models. We love to try to predict what's going to happen. Try to explain why things happen. That's what makes math fun. It's not just all these formulas and all this craziness. It's try to figure out where things are going and trying to figure out why things happened. And so there's a great example of that. Now here's the fun part. Let me ask you a question, probably about a numeric model or algebraic model, and then I'll see you in a few minutes. All right, nice work. Well, let's talk about another type of model. There's graphical models, as you see on your screen now, and you can see that it just looks pretty, and it usually helps a lot of people understand the data. This is data about your favorite dessert and what people chose, and 54 people answered, and this is how it broke down. And you can see that a lot of people like ice cream or frozen desserts or cookies, right? And that's why cream is so successful. I mean, look at how many people would just enjoy maybe the combination of ice cream and cookie. And if you're somebody who wants to open up a custard pudding place, probably not a good choice. But enough said, right? This is graphical data. Looks pretty. It gives us a nice way to see how much of something is represented. And then we can try to make an equation or a prediction of something like that, like how, I could try to figure out the percentage of people, or what's the chance that I ask the next person what their favorite dessert is, what's the chance that they say it's pie or ice cream. And, I can see it nice, and those are big options. Maybe you want to make a prediction of what the next person will say. Your best choice is probably to say ice cream, because that's the biggest group and it's easy to see a lot of people in there. So again, why do we like models? Because we want to solve. We want to get an equation that the data is there. We want to take all that data. We want to somehow figure out how we can give it meaning, and that's the math that we look at every day. So once you got yourself an equation, you're going to have to learn how to solve it. And so solving an equation can always be fun. Probably the most important thing to learn is when you solve equations, like you always have, you move everything over to one side so it equals 0, and then you solve it. Polynomials are, let's talk about quadratics for a minute. When you do a quadratic, you have different techniques to do. You learn the quadratic formula, you learned factoring, you learned the completing the square. So that kind of stuff will happen to you. And so you want to make sure that you know how to solve things. So let's go ahead and try one here. The zero product property, by the way, is when you have things that equal 0. If they're multiplied together, then that means one thing equals 0 or the other, right? This would be that either A is a 0 or B is a 0. One of them has to be 0 if they're multiplied together and equal 0. That's just understanding multiplication, right? Nothing fancier than what my daughter loves in her 3rd grade class, is being asked to multiply something by 0. And so you can enjoy it too, and that's what the zero product property is built off of. And don't forget your good friend, the quadratic formula. So here's an example. Look at that tough, we'd say we've got some data, we've racked our brains or used a calculator or a computer, and it spit out this model right here. It said, this will model your data. And you're like, sweet, now let's solve it. Maybe we need to know when this equals 0 for some reason. So that's exactly what I will do. First thing I'll do is I'll move that 4x over to the other side, and I'll move the 8 over. Now it equals 0. Now at this point, I usually try to factor, right? I got 3 terms, and 3 terms is a dead giveaway that you probably or try to factor. Now, how do you factor? I multiply the outside numbers, and I get -8. And I multiply, and I'll just look at the inside number, the one I haven't circled, and I get 4. And your job is to figure out what 2 numbers multiply to 8, or -8, that add up to 4. And if you can find those 2 things, this factors. So let me see, things that multiply to 8, or 8 and 1, no, that's not going to add up to 4. Well, obviously one of them is negative. 4 and 2, oh, that's not going to work. Darn it. This doesn't look promising. It is not factorable. Well, no big deal. Factoring is just the easiest, or I'm sorry, the fastest way. I shouldn't say it's the easiest. It's the fastest way. But there's other ways. We have the quadratic formula, right, where you know that this is A, and this is B, and this is C, and you plug it all in. So if you'd like, here it goes. X is equal to the opposite of B. So it was 4, so it's -4, plus or minus the square root of B squared, which is 16, minus 4ac, so a times c is negative 8, all over 2a. So I see this as negative 4 plus or minus the square root of, what is that, 16, 32, whoops, try to really write 32, all over 2. That's negative 4 plus or minus, is that 48, all over 2. Then I like to reduce that root 48. What the heck is that? Root 48 is, what do you think, 4 times 12? And 12 is 4 times 3. Ooh, look, a pair of 4s. I could have, yes, factored those down to 2s. I was just taking a shortcut that I saw a pair, and I'm like, bam, going to use them. So that's 4 root 3 for us. All right, so that's negative 4 plus or minus 4 roots of 3 all over 2. Now, again, I like to split this up. The little thing that you know about fractions is that you can break them apart, and so I will. And so I will call that negative 4 over 2 plus or minus 4 root 3 over 2, or what most of us will call negative 2 plus or minus 2 root 3. And we jump up and down and say, yay! There you go. Solved, done. For those of you saying, wait, what was completing the square? Let's talk about it real quick. X squared plus 4x minus 8 equals 0. How do I complete the square? Well, you move first of all, you move the thing that doesn't have your variable in it, you move it to the other side. So x squared plus 4x equals 8. Now the actual completing of the square. You take half of this term, which would be 2, and you square it, which would be 4, and you add 4 to both sides. Now, why on earth would you do that? Because that makes it factorable, right? This side now factors to x, or whatever your variable is, and half the middle number, so x plus 2. It factors to x plus 2 squared equals, what is that, 12? And now you continue to solve. Square root both sides, so you get x plus 2 equals plus or minus the square root of 12, which 12 happens to be 4 times 3, which is 2 root 3. So x plus 2 equals plus or minus 2 roots of 3. And then you subtract this 2 over, and you're like, oh, yes. Notice we got the exact same answer, but we should. So completing the square works because we know factoring, and quadratic formula works because we know the formula, and life is good. So let's talk about factoring real quick. I have this little thing, and I'm just going to kind of fly through it, but just to remind you that when you factor, always look for a greatest common denominator first and get that out. I'm sorry, greatest common factor first and get it out. If it has 2 terms, there's 3 things you want to worry about. Difference of squares, difference of cubes, sum of cubes. If it has 3 terms, you're going to do what I did. You're going to try to factor. You're going to try to figure out what 2 numbers multiply to the AC and add up to the B. That's very important. And we will do some of these in class, of course. And then number 4, if there's 4 terms, you will look for grouping. Remember, you do 2 at a time. You look at the first 2, you pull something out. You look at the second 2, you pull something out. And then hopefully you have common factors there. The big trick on understanding factoring by grouping is that when you factored out that first thing, these 2 highlighted sections better be the same. Otherwise, it's not factorable. Remember, things cannot be factorable. It happens, right? So don't worry about it. They can turn out to be prime. So be uber careful. All right. Now, why do we set things equal to 0? Just so you know, makes things true. If I set it equal to 0, it tells me that the number that we checked was a root or a solution of the equation. It also tells me it's a 0, another fancy word for the graph. Zeros of the graph tell me when the y value is 0. So hence it's called a 0. The answer to that when it equals 0, 2 is also an x-intercept of the graph. So it not only tells you when the y is 0, but it tells you the x-intercept. And those are usually, and most of the time, very important. And it also tells you, this one that I added on here, it also tells you that x minus a is a factor of that problem. So wow, when you solve things, you learn a lot of different things. You learn it's a factor, we call it a root, we call it a 0, call it an x-intercept, all the same kind of things. And very good to know. All right, that's a lot. I think we can wrap it up, except for I'm going to just mention graph or error. It's when you use your graphing calculator and you look at it and you trust it too much. Always remember on your calculators, make sure you learn how to zoom in and zoom out and see if the picture makes sense. Ask me if you don't know. We'll go over it in class, but I want you to make sure that you always, always, always check to make sure your graph makes sense. We're going to talk about a lot of graphs in the next couple of days. So let's make sure we're not getting tricked. That's it. Stay happy. Answer one more question, and I'll see you tomorrow, and we can practice some of this stuff. Have a great day.